exploring the potential consequences of very low grounding electrode impedance, specifically targeting 1 ohm, reveals a series of potential issues. Firstly, straight current may become a significant problem. A lower impedance path to ground encourages an increased flow of neutral current into the earth. This current spreads throughout the neighborhood, potentially interfering with underground utilities, pipelines, and other buried equipment. Secondly, animals may be at risk. If animals, particularly livestock, are standing on the ground, a potential difference could develop between their front and rear hoofs. This potential difference arises from the current flowing through the earth and can cause discomfort or even harm to the animals. Thirdly, corrosion is a concern. Higher current flow in the earth accelerates the corrosion of underground metal structures. Pipelines, water pipes, and other metallic infrastructure are susceptible to increased corrosion rates due to the presence of these ground currents. Fourthly, radio interference can occur. Ground currents are known to interfere with radio communications, especially at lower frequencies. This interference can disrupt radio signals and negatively impact communication systems. Fifthly, electromagnetic fields may increase. Increased current flow in the earth generates stronger electromagnetic fields. The potential health effects of prolonged exposure to these fields are a subject of ongoing research and debate. Sixthly, lightning protection might be compromised. While it seems counterintuitive, very low grounding impedance may reduce the effectiveness of lightning protection systems. Providing an easier path for lightning current to enter the building could lead to unexpected and potentially dangerous consequences. Now let's consider the benefits of maintaining a higher grounding impedance, such as 25 ohms. Firstly, stray current mitigation is enhanced. 25 ohms provides a barrier to excessive neutral current flow into the ground. This impedance level minimizes the potential for stray current issues and their associated problems. Secondly, hoof potential reduction is achieved. The higher impedance limits the potential difference between animal hoofs. This ensures a safer environment for livestock and other animals that may be present in the area. Thirdly, corrosion protection is improved. Reduced current flow in the earth helps mitigate corrosion of underground structures. The 25 ohms impedance level reduces the risk of accelerated corrosion and prolongs the lifespan of buried metallic infrastructure. Fourthly, electromagnetic field control is gained. Higher impedance limits the generation of electromagnetic fields from ground currents. This reduction in electromagnetic field strength minimizes potential health risks associated with prolonged exposure. In conclusion, while achieving very low grounding electrode impedance, such as 1 ohm, may seem appealing at first glance, it is important to carefully consider the potential consequences. Issues such as stray current, corrosion, radio interference, and potential harm to animals should not be overlooked. A grounding impedance of 25 ohms appears to be a reasonable compromise. It balances the need for effective grounding with the mitigation of stray current and other risks. However, it's important to note that electronic environments with a high likelihood of lightning strikes may require lower grounding impedance to enhance lightning protection. Always consult with qualified electrical engineers and adhere to local electrical codes to determine the most appropriate grounding strategy for a specific application.